Well, students, we have finished our discussion on secant method. In this lecture, let us study another method called Newton-Raphson method for approximating a simple root of a nonlinear equation. A natural question is, when we already studied secant method, why we have to study Newton-Raphson method? Well, if you recall, secant method iterative sequence has a fractional order of convergence. Its order of convergence is 1.62 approximately, we have seen. This method can be further modified to achieve quadratic convergence. That is, the order of convergence is 2. This modified version of the secant method is the Newton-Raphson method. What is this modification that brings in quadratic convergence? Let us see this. Assume that the secant method iterative sequence converges, then you can see that as n increases, xn minus 1 approaches xn, and therefore for large n of n, you can see that f dash of xn is approximately equal to f of xn minus f of xn minus 1 divided by xn minus 1, right? So I'm just applying the definition of the first order derivative of a continuously differentiable function. Now, why am I telling this? Well, if you recall, the formula for the iterative terms of the secant method is given by this. From here, this term is sitting here in the denominator of the second term, right? Now the question is, what is going to happen for a large n? Why can't we substitute this in the place of this term right from the first term of the sequence itself? That is the question. That is, why can't we consider this as our formula to generate the iterative sequence of the method? And this is the main idea behind the Newton-Raphson method. And this is the formula used to generate the iterative sequence of the Newton-Raphson method. Let us formally derive this formula. Assume that we are given a real number x0. Consider the Taylor polynomial of degree 1 for the function f of x. You can write f of x as the Taylor polynomial plus the remainder term, right? The idea now is to ignore the residual term and try to approximate your function f by this linear polynomial, and thereby, instead of solving the equation f of x equal to 0, you solve this linear equation f of x0 plus f dash of x0 into x minus x0 equal to 0. Now you call the root of this equation as your first term of the sequence. That is, call it as x1, and from here you can get x1 equal to x0 minus f of x0 divided by f dash of x0. This is what we have also proposed as a formula, taking the motivation from the secant method. The same formula is now achieved by the process of linearizing the function f. This process is called linearization of a nonlinear function, and that is why Newton-Raphson method is also often called linearization technique. Let us now write the algorithm for Newton-Raphson method. Assume that the function f is a C1 function because we need to basically include the derivative of the function f in our formula. Therefore, to implement the formula, we need the function f to be differentiable. And as usual, we'll assume the root that we are interested to capture is a simple root. And also we assume that x0 is chosen pretty close to the root r. Well, this is an assumption generally made for the theoretical purpose. However, practically we don't know the value of r, therefore we don't know what is mean by choosing sufficiently close to r, right? Therefore, when we implement the method, generally we tend to choose x naught arbitrarily, but in order to make sure that the sequence converges to the root r, you have to put such assumptions. Well, this comes later in the convergence theorem. Let us first go ahead with the algorithm. You are given x naught, then for every n equal to 0, 1, 2 and so on, we define the Newton-Raphson's iterative sequence as xn plus 1 equal to xn minus f of xn divided by f dash of xn. Well, coming to the stopping criteria, as I told in the previous lectures, we have already discussed the stopping criteria for regular falsy method. The same stopping criteria will hold for any method that we will be discussing in this chapter. If the stopping criteria is satisfied, then we will stop the iteration. Well, this is especially important when you are implementing the method on a computer. If the stopping criteria is not satisfied, then you will keep on generating the terms of the sequence until you achieve the stopping criteria. So that is the algorithm for Newton-Raphson method. Let us take up our usual example, sin x plus x square minus 1 equal to 0. Now we will start our initial guess with x naught equal to 1. You can clearly see from the iteration that unlike secant method, for Newton-Raphson method, we need only one initial guess, right? That is why we have taken x naught alone. You don't need any more information to start the iteration from the computational point of view. So once you have x naught, you have to evaluate the value of the function f at x naught, and not only that, you have to also evaluate the value of f dash at x naught and then use this formula to generate x1, and that is given by this value. The error involved in x1 when compared to the exact root is given by 0.03. Then when you go to find x2, you have to use the formula x1 minus f of x1 divided by f dash of x1, and that gives this value, and you can go on like this. If you recall, we got the error to be 0 up to 6 digits in the secant method at n is equal to 5, right? Whereas in Newton-Raphson method, we achieved the accuracy up to 6 digits at the third iteration itself in this particular equation. That gives us a feeling that Newton-Raphson method may be converging much faster than bisection method and secant method. Well, in fact, it is true in certain cases. Under certain hypotheses, in fact, we can show theoretically that the order of convergence of the Newton-Raphson method is 2. Graphically, how this Newton-Raphson method works, let us see. Suppose the graph of the function f is given like this, and suppose you have given x naught somewhere reasonably close to the root of the equation f of x equal to 0, then what this Newton-Raphson method iteration does is it takes the tangent line at the point x naught and look at the point of intersection of this tangent line with the x-axis, and that it takes as the point x1, and once you have x1, again you take the point x1 comma f of x1 and draw the tangent and see the point at which it intersects the x-axis, call this as x2 and so on. Why it is a tangent line? Because if you recall in the derivation of Newton-Raphson method, we have taken f of x and linearized it, and took f of x naught plus x minus x naught into f dash of x naught equal to 0. So we considered this equation, right? In that way, we are looking at the tangent line of f at the point x naught and seeing where it touches the x-axis. And that was the idea of Newton-Raphson method, and that is how we obtained x1, right? So geometrically, therefore, it has to be like this. In this graph, the blue solid line represents the graph of the function f of x equal to sine x plus x square minus 1, and the straight line is the tangent line at x naught equal to 1. That is this point, and the point of intersection of this line with the x-axis is what we obtained as x1. Let us now try to prove the convergence theorem for Newton-Raphson method. The statement and the idea of the proof are more or less the same as we did in the secant method. The hypotheses of the theorem are as follows. Let f be a C2 function, and the root that we are interested in is a simple root for the nonlinear equation f of x equal to 0. It means f dash of r is not equal to 0. Given these two conditions, what the theorem concludes that there exists a delta such that whenever you start your iteration, that is the value of x naught is chosen in the delta neighborhood of r, then all the terms in the sequence xn generated by the Newton-Raphson method are well defined. Further, the sequence xn is contained in the interval r minus delta to r plus delta, and also the sequence xn converges to r. In fact, we can also show the order of convergence of the Newton-Raphson method to be 2. That is, Newton-Raphson method has quadratic convergence. And in fact, just like in the case of secant method, we can show that limit n tends to infinity mod xn plus 1 minus r divided by mod xn minus r square is in fact equal to constant, and that constant is given by f double dash of r by 2 times f dash of r modulus. That is what we have also shown in the secant method, where this power was 1.62 approximately in the secant method, but here it is 2. We'll try to prove this theorem. As I told, the underlying idea of the proof is more or less the same as we did in the secant method. A good thing is that in Newton-Raphson method, the proof is much simpler than the secant method. As a first step, we will derive this expression which says that for n equal to 1, 2, and so on, if the corresponding xn is not equal to r and f dash of xn, sorry, there is a typo here, f dash of xn is not equal to 0 because that has to sit in the denominator, then we have to show that there exists a parameter xi n such that xn plus 1 minus r is equal to xn minus r the whole square into f double dash of xi n divided by 2 times f dash of xn. Let us see how to prove this statement. Recall that the formula for generating the iterative sequence of Newton-Raphson method is given by this, and in this we will take r minus xn plus 1, and that will be given by r minus xn minus f of xn divided by f dash of xn. And this can be rewritten like this. Now we will try to use the Taylor expansion of f of r to get a equivalent expression for the numerator of the equation 1. If you recall, we can write f of r is equal to f of xn plus r minus xn into f dash of xn. This is the Taylor polynomial of degree 1 plus the remainder term, right? Now, since f of r equal to 0, we can write f of xn plus r minus xn into f dash of xn is equal to minus f double dash of xi n divided by 2 into r minus xn the whole square, which is the remainder term. I'm just taking it on the other side of this equation. Now substitute this term here to get what we actually want to show. Remember, the xi n that we obtained here lies between r and xn, which comes from our remainder term. Now let us see how to use this expression to prove the conclusions of our theorem. Recall that we have assumed our root r as a simple root of the equation f of x equal to 0, and also we assumed that f is a C2 function. Therefore, in particular, f dash is continuous. Let us use these two assumptions to find a delta neighborhood of R in which f dash never vanishes, and then we choose a delta less than delta naught such that m by 2m into mod x naught minus r is strictly less than 1 for any choice of x naught in the delta neighborhood of r, where the delta is not delta naught, but it is some delta less than delta naught such that this holds, where small m is the minimum of f dash of xi for all xi in this delta neighborhood, which is always not equal to 0. Since delta is less than delta naught, we can see that this is a subset of your interval on which f dash never vanishes, right? Therefore, in this interval also f dash is not equal to 0. Hence, small m is strictly greater than 0. And we take the capital M as the maximum of f double dash of zeta for all zeta is again coming from this restricted delta neighborhood of R. And without loss of generality, we can assume that capital M is greater than 0. If you recall, we have mentioned the reason for why we can assume this positivity of M without loss of generality. In a similar situation, while proving convergence theorem for secant method, let me recall it once again. If capital M is equal to 0, it means what? It means f double dash of zeta is equal to 0 for all zeta in this delta neighborhood, right? It means f dash is constant in this interval, and that means f is a straight line. That is, it is a polynomial of degree 1 in this interval. And remember, for any given f, we are approximating f by polynomial of degree 1 and then solving it to get our xn, right, in the Newton-Raphson method. It happens to be the tangent line, if you recall. That is what the geometrical interpretation of the Newton-Raphson method. On the other hand, if f itself is a straight line, then your xn will be equal to r, right? In particular, if you are choosing your x0 in that neighborhood where f is a straight line, then x1 is equal to r. So we have nothing to prove because at the first iteration itself, we obtained the exact root, right? Therefore, there is nothing to prove in this case, and that is why we assume m strictly greater than 0, in which case it becomes non-trivial and we need to prove something, and hence without loss of generality, we are assuming capital M to be positive. Recall that as the first step, we have proved this expression. Take modulus on both sides. You can see that mod xn plus 1 minus r is less than or equal to xn minus r the whole square into modulus of this. And if you remember, we have taken capital M to be the maximum of f double dash in the interval. Therefore, we are replacing f double dash by maximum, and we have taken small m to be minimum of f dash in our delta neighborhood. Therefore, we are replacing f dash in the denominator by minimum. Therefore, this entire thing will be less than or equal to. That is what we have written here. Therefore, this inequality is clear for us. Once you have this, you just take n is equal to 0 and look at this inequality. You will have mod x1 minus r is less than or equal to m by 2m into x0 minus r the whole square. That I'm just writing like this. And now I'm using the fact that this is less than 1, because that is how we have restricted our delta neighborhood and chose our x0 in that delta neighborhood, right? So that is what we have done here. That I will use for the first part. And second part is, after all, x0 is coming from our delta neighborhood, therefore it is less than or equal to delta. So combining these two, we can say that mod x1 minus r is strictly less than delta, and that implies that x1 belongs to the delta neighborhood that we chose. Now the same argument can be repeated, and we can bring in an induction argument to show that xn belongs to the delta neighborhood that we have chosen. In fact, we can say that xn belongs to the open interval. In fact, this proves one of our conclusions, that whenever we choose our x0 in the delta neighborhood, then the sequence xn will be contained in that delta neighborhood. It means each xn will belong to that delta neighborhood, and the conclusion 1 can also be obtained very easily from here. Why? Because basically we have chosen this interval r minus delta to r plus delta in such a way that f dash of xi is not equal to 0 for all xi in this interval, right? That is how we have chosen this interval. Since all xn's are contained in this interval, we can in fact say that f dash of xn is not equal to 0. And if you recall, this is the only way that our iterative sequence can fail to take finite value, right? So therefore, as long as we choose our x0 in this delta neighborhood, we see that all the xn's are well defined. So we have finished proving two conclusions. Let us prove the convergence now. Coming to the convergence part, you again take up the inequality that we have derived, and we can see that the right hand side can be written as delta times m divided by 2m into mod xn minus r. What I'm doing, I'm just keeping m by 2m into one term, that is mod xn minus r as it is, and another one term mod xn minus r, I'm just using the fact that xn belongs to the delta neighborhood. Therefore, I'm just replacing it by delta, and thereby I will have, sorry, there is a less than or equal to sign here. In fact, it is strictly less than. Now, once you have this inequality, you can apply the same inequality to xn minus r. And you see that this is less than or equal to m by 2m times delta into mod xn minus 1 minus r, right? That is this term alone I'm saying. That when combined to what is already there here, you can say that this entire right hand side is less than or equal to delta by 2m, the whole square, into mod xn minus r. Again, apply the same inequality to this term and get this is less than or equal to delta into m by 2m, the whole square. Then one more term will come from here, therefore whole cube mod xn minus 2 minus r. Now you continue this till the end, and at the end you have delta into m by 2m, the whole power n plus 1 into mod x naught minus r. Now remember, we have chosen our x naught such that this term is strictly less than 1, right? If you recall, that is what we have chosen here. Remember, we have chosen x naught in this neighborhood, therefore this is less than or equal to delta, right? Therefore m divided by 2m into delta is strictly less than 1. That is what I'm trying to say here, and that is raised to now n plus 1. Now what can you say about this term as a sequence when you take n tending to infinity? Well, you can see that this entire term goes to 0 as n tends to infinity. That means the right hand side is going to 0 as n tends to infinity, and that proves the convergence of the sequence xn generated by the Newton-Raphson method. And now how will you prove that limit n tends to infinity mod xn plus 1 minus r divided by mod xn minus r, the whole square, is equal to mod f double dash of r divided by 2 into f dash of r? Well, I leave it to you to prove this, because the idea behind this is exactly the same as we have done with the secant method. We have completed the proof of the Newton-Raphson method convergence theorem. In this theorem, the main part is that if we start nearby a root of the nonlinear equation, then Newton-Raphson iterative sequence is well defined and it converges, right? This is the main takeaway from this convergence theorem. How near we have to choose? Well, there is a way to do that, which is explained in the proof itself. Well, if I don't start my iteration nearby, that is, if I don't take my x naught in a sufficiently chosen delta neighborhood, then what happens? Let us try to see this graphically. Assume that the equation f of x equal to 0 is in such a way that the graph of the function f is given like this, and we are interested in getting an approximate value of the root of this equation. So if I start my iteration very close to r, you can see that I can in fact converge to this. Say for instance, if I take here, then the first iteration will be here x1, and the second iteration will be something like this, x2, and so on, right? So it will start converging towards r. Now what if I go little far away from the root and say take something here? It may happen that, just assume that this is the slope of the graph at the point x equal to x naught, and at this point, the slope of the graph, say for instance, it is going like this instead of this, then the slope of the function at x1 might become 0, right? So this kind of situations can happen. That is why the theorem gives you guarantee of the convergence only in a sufficiently small neighborhood of your root. If you go far away from the root, well, things may not be in our favor. That is what is the reality. But there are certain particular cases where you don't need to really worry about starting your iteration very nearby. For instance, if your function is an increasing convex function, we need not be very careful in choosing our initial guess. It means, suppose the graph of the function is something like this. It just goes on like this. It's a convex function and it's an increasing function. Then anywhere I choose, even my x naught very far from this, I may be, and now it will be going like this because it's convex function. Assume that it's convex. Then you have x1 here, x2 here, and so on. In fact, you can prove this, and not only increasing convex function, you can also conclude the same for decreasing convex function or increasing concave function, decreasing concave function also. So in such functions, the Newton-Raphson iterative sequence always converges, whatever may be the initial condition. However far away you go from the root, your sequence will surely converge. In fact, for sufficiently large n, your sequence will be a monotonic sequence. That also you can show. Let us just state the convergence theorem for this particular case of convex function. Let f be a twice continuously differentiable function such that f is convex, which is equivalent to saying that f double dash is strictly greater than 0 for all x belongs to R, right? So this we know from our basic analysis, and f is strictly increasing. Similarly, you can also prove the same theorem for convex strictly decreasing, concave strictly increasing, and concave strictly decreasing. All these particular cases have this luxury, and of course you have to assume that there exists a R such that f of R equal to 0. That means the equation f of x equal to 0 should have at least one root, right? Otherwise, we cannot expect our Newton-Raphson method to converge, right? That is quite obvious. Then we can right away say that R is the unique solution of the nonlinear equation. Of course, because it's a monotonic function, this conclusion is really not a part of the numerical analysis. This can be a good exercise problem in the calculus course. Further, the second conclusion is a numerical analysis exercise. It's an easy exercise which says that for any choice of x naught, not necessarily in a small neighborhood of R, you choose any x naught, the Newton-Raphson iterative sequence converges to R. I'll leave it to you to prove this. Not only this, the other three cases also. That is convex strictly decreasing, concave strictly increasing, and concave strictly decreasing also. You can prove in a similar way. It's a very easy exercise. You have to learn how to prove them. Recall that we have shown the Newton-Raphson method has quadratic convergence. Remember, when we were proving quadratic convergence, we have assumed that R is a simple root, right? Therefore, don't think that Newton-Raphson method is always a quadratic convergent method. Say, for instance, if your function is something like this, then your theorem doesn't say that the Newton-Raphson method will converge with quadratic convergence. Therefore, before concluding that your Newton-Raphson sequence converges quadratically, you have to first check that f dash of R is not equal to 0, provided if you know what is R. Of course, theoretically, we can give a value of r, which is the root of your equation f of x equal to 0, and see if the Newton-Raphson method will converge quadratically or not. What we have to do is we have to first check whether f dash of r is not equal to 0. If it is so, then we will say yes, it converges quadratically. Otherwise, we cannot say that it is quadratically convergent, right? That is one subtle point that we have to keep in mind.